I can start again. So my great pleasure to introduce Ehud De Shalit from Jerusalem, who will speak of moduli of p-divisible groups.
Okay, so thank you very much. I want to thank the organizers for inviting me to this beautiful place. It's my first time in India, and I'm excited. So this will be a series of 5 talks on the subject of moduli of p-divisible groups. And this is, of course, an old subject which started about 50 years ago with Lubin-Tate and contributed a lot in many branches of arithmetic and geometry, mostly in the theory of Shimura varieties and moduli of abelian varieties, and in p-adic Hodge theory, as we will see this week. But in the last 10 years or so, there was a new twist, and this was mostly with the introduction of perfectoids and all that goes around it, and also with what I would call the geometrization of p-adic Hodge theory with the Fark-Fontaine curve, which sheds new light on old results. So the plan of these 5 talks is to have really a survey, and I apologize for not being able to give many proofs, because I'd like to give a broad survey starting with finite flat group schemes of the subject in the first 3 talks. And in the 4th and the 5th, the Fark-Fontaine curve will show up. Hopefully by then, Kiran and Denis will have mentioned it too, so we will try to coordinate our courses. And then we will see how the new developments shed new light on the old results. So for today, I want to really spend about half of the hour with background on p-divisible groups and formal groups and the relation between the two. So these are the 2 backgrounds that you see here. And then the remaining 20 or 30 minutes about the Lubin-Tate tower, the Lubin-Tate moduli space, and the tower that accompanies it. And this will be our leading example, although we will see more examples later on. So let us start with some motivation, and this is the only time I will mention abelian varieties, at least today. If you start with a single abelian variety over a field K, and L is different from the characteristic of the field, then, as you all know, you have the Tate module of the abelian variety, which is isomorphic to ZL to the 2G, G being the dimension, with a continuous action of the Galois group. And this continuous action, at least if the field K is small, tells us quite a lot about the abelian variety. For example, Tate in the case of a finite field and Foltings in the case of a number field show that it determines the isogeny class of A completely. As another example, we have the famous theorem of Og, Neron, and Shafarevich that says that you can learn where A has good reduction. You want to see, in the case that K is a number field, you want to see if A has good reduction at V. You look at the representation, and provided V doesn't lie above L, the criterion is that A has good reduction if and only if this representation is unramified at V. However, if you want to study families and deformations over a p-adic base in characteristic P or p-adically, then this homology, the L-adic homology of A, is inadequate simply because the L-adic topology of the local system and the p-adic topology of the base, or the mod P topology, do not speak to each other. So if you're familiar with Hodge theory of the complex numbers, well, one does the same thing. Everything is complex. They do speak to each other. Here they do not. So you may ask, why not use the p-adic Tate module? It's simply too small. Okay, as you know from the case of the supersingular elliptic curve, it may be even 0. So the solution in this case is to consider the whole p-divisible group that we will define, which is a fantastic replacement for the p-adic Tate module. And in fact, the famous theorem of Sayre and Tate says that given an abelian variety over a field of characteristic P, the category of deformations of A is naturally equivalent to the category of deformations of the p-divisible group. So as far as deformation theory is concerned, you may study, instead of the formations of A, the formations of its p-divisible group. So this was only a motivation. And let us start from the very basic. What is a finite flat group scheme? So first of all, we have a ground ring R, and we have some finite locally free. Actually, if the base is non-Noetherian, flat is not enough. It has to be locally free. Scheme spec A, affine, and it has a group structure. So group structure as a group scheme is reflected, as you know, in general algebraic geometry, in dual maps on the ring level, and these are the co-multiplication, the co-inverse, and the co-identity, and they satisfy certain diagrams that you can write yourself if you haven't seen them, that turn A into what's called a Hopf algebra. So that's just a definition. And then we have some examples, and I assume that you've seen them, but let's go quickly over these examples. First of all, to any finite abelian group gamma, you can construct a constant group scheme whose Hopf algebra is just R to the power gamma. You have the nth root of unity group scheme, UN, and in characteristic P, the famous group scheme alpha P, both of which are given very explicitly. You can really write down the Hopf algebra explicitly. Less explicit, of course, is maybe the most interesting example of the kernel of M on an abelian variety of dimension G. And the rank of A as an R module is called the rank of the group. In the last case, it's M to the 2G. And it will be very important for us to adopt the functorial point of view right from the beginning. So a finite flat group scheme leads to a functor from the category of R algebras to abelian groups, which happens to be actually a sheaf for the FPPF topology. But we'll not use this topology that much. But it's important because often we will be defining group functors and asking whether they are representable. Sometimes they will be, sometimes they will not be. Now, if you look at this Hopf algebra A, and you write all these diagrams that I avoided intentionally, you see that there is a duality staring in your face. Okay, the structure morphisms, homomorphisms that describe the algebra structure are dual in a sense to the ones that describe the co-algebra structure, the ones that I called co-multiplication, co-inverse, and co-unit. And the way that this works is that if you take the R dual as a module, okay, you can use the algebra structure on A to define a co-algebra structure on a dual and vice versa, and thereby to get a new Hopf algebra that leads to a new finite flat group scheme, because this is, of course, also finite and locally free. And you may ask what functor it represents. So it represents the functor that sends any R algebra S to the homomorphisms as S groups in the category of S groups between the base changes of G to S and of the multiplicative group to S. This is, of course, very different than the S points, the homomorphism from the S points of G to the S points of GM. And the dual of, this is called the Cartier dual. And it's evident that the Cartier dual of the Cartier dual is the group itself. Mu n is dual to Z over nz, alpha p is self-dual. And in the case of the abelian variety, the dual of kernel of M on A is the kernel of M on the dual abelian variety, and this is basically the veil pairing. The second concept that I'd like to recall is the Lie algebra. So this works not only for finite flat group schemes, but in fact for any group functor. For any group functor G, you can make this definition. R epsilon is, R is our ground ring as before. R epsilon is the ring of dual numbers. So epsilon squared is 0. So it's R plus R epsilon. And you look at the R epsilon points of G that when you reduce mod epsilon give you the identity. and this is the Lie algebra. It acquires an additive structure from the group operation of G and an R module structure as well. I described how. And when you think really in concrete terms what it is, then on the Hopf algebra level, such a thing is given by a homomorphism from A to R epsilon that mod epsilon reduces to the co-unit. So all that remains is the coefficient of epsilon. The coefficient of epsilon is some linear functional on A, and you check what it means. It's simply a derivation centered at 0. And derivations centered at 0 are, as you all know, canonically the homomorphisms from the cotangent space at the origin into R. So this is the Lie algebra. Then we have the important notions of étale and connected group schemes. So G is étale if this cotangent space at the origin is 0. And this is equivalent to saying that after a finite étale base change, it becomes constant. And it's connected if it is connected. There's a scheme if A has no idempotence other than 0 and 1. And over fields, and more generally over Henselian local rings, where you can lift idempotence from the field to the Henselian ring, there is a canonical connected étale exact sequence. In a moment I will say what I mean by an exact sequence, because I've not made it clear yet, where the first comes the connected part and the quotient is étale, and moreover, if R is a perfect field, this sequence splits canonically. You can, in the case that R is a perfect field, you can identify inside G, it's reduced. You can always take the reduced scheme, but in this case, it acquires a group structure, and it is a closed subgroup scheme that maps isomorphically under reduction modulo G0 to the étale part. Now, I've said that there is a connected étale exact sequence. The category of finite flat group schemes over R is obviously an additive category, but in general not abelian unless R is a field. So what do we mean by an a short exact sequence? Well, either you go to the point of view that I emphasized before is important of sheaves, and you just say that it is exact as FPBF sheaves, or specifically it means that alpha is a closed immersion, beta is faithfully flat, and alpha is the morphism alpha is the kernel of the morphism beta. So much for finite flat group schemes, and now we come to p-divisible groups. A p-divisible group, and I adopt Tate's definition. There are various definitions, but this is basically Tate's definition of height h. There will be a height associated to it over our ground ring R is a system Gn, In, and Pn, where Gn is a finite flat group scheme of rank p to the nh. In is a close embedding, close immersion of Gn in Gn plus 1, identifying Gn with a p to the n torsion on Gn plus 1. And Pn is multiplication by p, but so to speak, you go from Gn to Gn minus 1. So to view it really as multiplication by p inside Gn, you have to follow it by the inclusion of Gn minus 1 back into Gn. So actually, this Pn is forced upon you from the knowledge of In, but I want to include it in the definition because for Cartier duality, it's very symmetric. You'll see in a moment. Sorry? Right, but yeah, so, right, exactly. Yeah, I mean, I cannot write it down right now, but it comes up all the time when you study group schemes in abelian varieties and so on. Yeah, So for arbitrary rings and things can go wrong. Yeah. Okay. So I should have said that a finite flat group scheme. Yeah, I think this actually. Right. It is. Yeah. Yeah, no, but what I want also to say, yeah, it follows from this. Yeah, it's too concise, but no, but what I also wanted to say is that, yeah, maybe that's not relevant to here, but a finite flat group scheme is always killed by its order, but that's not it will not do it here. Yeah, okay, good. No, but that was it. Okay, so we can talk, of course, about G being the direct limit or the union of the GNs. So that's an example, for example, of an FPPF sheaf that is not representable. There's no group scheme that represents mu p to the infinity. The examples that are most familiar are QP over ZP, mu p infinity, the p to the infinity torsion on an abelian variety. Notion of short exact sequence carries on from finite flat group schemes to p-divisible groups. And the Cartier duality carries over when you take for the new in the dual of the p, well, n plus 1, because it goes from level n plus 1 to level n. So for the new p, you take the dual of I. So if you take the system of Cartier duals of the GNs and you invert the roles of the i's and the p's, you dualize them, then you get a new p-divisible group. The dual of mu p infinity is qp over zp, and so on. And how about the Lie algebra? So I haven't said it, but the Lie algebra of a finite flat group scheme can be very nasty. Okay, it need not commute with base change. It need not be locally free. Just take mu2 over base r, and the Lie algebra is the kernel of 2 on r, and this is pretty nasty sheaf. But the Lie algebra of a p-divisible group is already very well behaved. And for that, let's assume first that p to the n is 0. And since gn is the kernel of p to the n on gn plus 1, of course, Lie gn by the definition is the kernel of p to the n on Lie gn plus 1. But as long as n is greater than or equal to capital N, this is everything, right? Because p to the n kills r. So this thing stabilizes, and you call this common module Lie G. Later on, we will go to the limit, but when p is only topologically nilpotent. And this, as I said, is very well behaved. It's a locally free sheaf. Sorry, it's a locally free module of rank D that is less than or equal to h. That was the height of G, and this D is called the dimension. That's how you define the dimension of the p-divisible group. It behaves well with respect to base change. The Lie algebra of the base change of G is the base change of the Lie algebra. And the dimension of G plus the dimension of its Cartier dual always add up to the height of G. So for example, in the case of mu p infinity, the dimension is 0, the Cartier dual is qp over zp, its dimension is 1, dimension of qp over zp is 0, and together they add up to 1. In the case of an abelian variety, this p-divisible group is polarized, is self-dual or up to isogeny self-dual, and each of the dimension of the p-divisible group and its dual is the dimension of the abelian variety, and the height is twice the dimension of the abelian variety. And also the connected étale exact sequence carries over from the finite GNs to the whole p-divisible group and splits as before if R is a perfect field. And in fact, something that I could have mentioned before, if you also use over a perfect field this splitting for the Cartier dual, then you get over a perfect field of characteristic P that every p-divisible group breaks up canonically into a multiplicative part, a product of a multiplicative part, a bilocal part, and an étale part, where the multiplicative is such that it is connected, but its dual is étale, and the bilocal is such that it is connected and its Cartier dual is also connected. And then we have the very important notion that will show up a lot in this course of isogenies. So the homomorphisms between two p-divisible groups has no p torsion, is a flat ZP module. That should be obvious from the definition. So we can form a new category called the category of p-divisible groups up to isogeny. It's a long name, where you take the same objects, but you replace the Holmes by the Holmes tensored with Q. Okay? So the new Holmes are Holmes where you invert P, and an element in such a category, a homomorphism in such a category will be called a quasi-homomorphism, and a quasi-isogeny is a quasi-homomorphism which is an isomorphism in this category. So that's a very, again, a very concise definition. All that it means is that, first of all, after you multiply it by some power of p, it becomes a true homomorphism. Then it's not only called a quasi-isogeny, but an isogeny that is surjective and has finite kernel. And if G and G prime are isogynous, then they share the same height and the same dimension, and the kernel of an isogeny is a finite flat group scheme. And any quasi-isogeny has a height associated to it. The height of the p-divisible group is the height of the quasi-isogeny multiplication by p. But you can assign to any quasi-isogeny a height. If this quasi-isogeny is a true isogeny, a true homomorphism, p to that height is the rank of the kernel. And in general, you can work it out if you insist that this nice equation continues to hold. And the very famous and useful isogenies to have in characteristic P, if R, so far R was general, but if R now is an FP algebra, then you have the relative Frobenius, which you have for every scheme. Here becomes an isogeny. And what's special in the group situation that you also have the Verschiebung. The Verschiebung is defined in the following way. You take the Frobenius of the Cartier dual and you dualize this. So instead of going from G to its P transform, it goes from the P transform to G. And Frobenius composed with Verschiebung is multiplication by P. So this is a very short review of p-divisible groups. And the second topic that I wanted to review, which is closely connected, is formal groups. And they're so closely connected that are often mixed up with each other in the literature. And so to speak, when people do math, they always pass. But I would like to really define formal groups and say in what way they're the same sometimes as p-divisible groups. And for that, we have to make a little detour into adic rings. There will be much more talk about adic rings, but here is a concise definition. An adic ring is a complete and separate topological ring R, for which there is an ideal I, so that R topologically is the inverse limit of R over I to the n. So of course the intersection of all I to the n is 0, and R is iodically complete. But the ideal I is not part of the data. You can take many different ideals that give you the same topology, and every such ideal is called an ideal of definition. And you easily see, since the powers of I form a system of neighborhoods at the origin, that J is also an ideal of definition, if and only if I contains a power of J and J contains a power of I. So here are examples. Any discrete ring with I equals 0 is an adic ring. So the category of adic rings contains the category of discrete rings. The completion of any ring with respect to a finitely generated ideal. Funny things can happen in non-Euclidean rings when you complete with respect to non-finitely generated ideals. Is an adic ring. I mean, a completion of the power series ring over K in infinitely many variables is not complete. You can take the polynomials over ZP in U and you complete it either with respect to the ideal generated by P and U, and then you get the power series, or you can complete it only under the ideal powers of the ideal P, and then you get the power series whose coefficients go to 0. Observe that the first ring is also a p-adic ring. It also carries a different topology. It's also complete in the p-adic topology. And if R is adic, we will denote by nil of R the ideal of topologically nilpotent elements. So why do we give it a special name? Because these are the elements that we would like to substitute in power series, hoping that they will give us a meaningful quantity, and they will, exactly because the ring is separated and complete. So power series converge when you substitute topologically nilpotent element. Topologically nilpotent simply means that powers of those elements go to 0. Let me just warn you that nil R itself, if R need not be an action. Think of CP that was introduced this morning. So in OC, the nil of OC is MC, the maximal ideal, but all the powers of the maximal ideal are the maximal ideal. So let's start with the naive notion of a formal group law. So if R is adic, and A is the power series ring over R in D variables, a D-dimensional commutative formal group law over R is just a D-tuple of power series in 2D variables that I call x1 up to xd and y1 up to yd. That satisfies formally 3 requirements. First of all, there is no constant term. This allows you already to substitute power series iteratively, one into the other. Then 2 and 3, of course, mirror the requirements for commutativity and associativity. Now you may ask, why didn't I include the existence of an inverse? Because that's a formal consequence. It's a very easy exercise. You just build it term by term. And examples, the additive formal group law is x plus y. The multiplicative is not x times y, but is x plus xy, because we have shifted the origin to 1. So this is 1 plus x times 1 plus y minus 1 to get back to 0. And if you take an abelian scheme over R, and you take the completion of its local ring at the origin, O is here, the origin of the abelian scheme, and you use a regular system of parameters, then you get a formal group law. That depends, of course, on which parameters you used. Now, anytime you have such a formal group law phi, it gives you a functor that I will denote script G. So script will be for formal groups, and non-script will be for p-divisible groups in this series of lectures. Script G phi, which goes, it's a functor from adic rings over R. So these R itself was adic, and adic over R is the category of adic rings with a morphism in the category of adic rings, continuous morphism to R. Okay? So it's the relative category over R, 2 abelian groups. As I said, you plug in for each of the variables an element from nil S, a topologically nilpotent element in that adic ring S, and you get a set, and what is your addition law? Is the one given by phi. And the Onetta lemma, as usual, as always, tells us that this functor determines phi up to isomorphism, and we can now have an ad hoc definition of a formal group. Some people give a much more fancier definition. If you look up the book by Messing or Grothendieck, they give you fancy definitions, but for us this will be good enough. A formal group G over R is a functor from adic over R to ab, which locally on R is of the form G phi. Of course, R can be spread out, need not be local, so maybe you cannot use the same coordinates everywhere, but locally Zariski on R, it should be a functor of this form. And now we come to a very important definition. A formal group G phi is called p-divisible if multiplication by p, so I denote it by square brackets p, is a finite flat morphism, which means, of course, that the pullback on the ring level exhibits A as a finite flat or finite locally free module over itself. Okay, so if you are in dimension 1 and you look at GM, this is p-divisible. Why? Because multiplication by p is 1 plus x to the p minus 1, which is px plus x to the p, which is evidently, right, it's, yeah. 1x up to x to the p minus 1 is a basis over the image of A under this. But GA is not, okay, because multiplication by p is p times x, that's not finite flat morphism. And it's a fact that takes a little effort, not too much, but that's maybe the first non-trivial fact in all that I was saying. It takes a little effort to prove that the degree, I mean, in dimension 1 it's easy, but in general it takes a little effort, that the degree of p is always a power of p to the h, and this h is called the height of the formal group. GA, for example, sometimes is said to be of infinite height. So how is the theory of formal groups related to the theory of p-divisible groups? Let G be a p-divisible formal group, one that I just defined. Then we can define a collection of finite flat group schemes, Gn. We first define them just as functors, as presheaves. Okay, what they do to each S in adic R, it's the kernel of p to the n with the obvious inclusion and the obvious multiplication by p. And the theorem is that this is, in fact, this functor is a p-divisible group. It's represented by a p-divisible group. And the functor that takes a p-divisible formal group to this p-divisible group in the sense of Tate is a fully faithful functor from the category of p-divisible formal groups onto a full subcategory that obviously we will call formal p-divisible groups. So the two adjectives have changed their order. Okay, either we start with a formal group that is p-divisible, or you obtain a p-divisible group that is by definition formal. And in the case where we have described connected and étale exact sequence, being formal is the same as being connected. And the two definitions that we gave for height or for the Lie algebra, well, the Lie algebra of G, if P is not nilpotent, now will be defined as this inverse limit. Previously, I assumed that P to some power n was 0. But now, if remember, all our rings are adic over Zp. Always P is topologically nilpotent in all that we will be doing. So the two notions of height and dimension or Lie algebra coincide. But there's one annoying point, and this is that the notion of points is not always the same, so we actually redefine the notion of points for a p-divisible group. So let R be now an adic ring over Zp, and S an adic ring over R, and let's take any ideal of definition IS of S, and if G is a p-divisible group over R, we redefine G of S to be the inverse limit of G of S over IS to the n. So in S over IS to the n, you lost the topology. It's a discrete ring. If S was discrete to begin with, you have not changed the definition. You have also not changed the definition if G was étale, because if G is étale, of course, the points of G G in S over IS to the n and S over IS to the n plus 1 are the same, right? That's one of the basic things about étale. But if G is connected, for example, and it comes from the formal group script G by the process that I described yesterday, not yesterday, previously, due to Tate and Messing, then the new notion gives you the points of the formal group. So as an example, let's see how it works in the multiplicative case. Mu p to the infinity of OC, of the ring of integers in CP, in the old definition would just all p power roots of unity. but now it will be the inverse limit of mu p to the infinity of OC over p to the n. Mu p to the infinity of OC over p to the n is just 1 plus MC modulo p to the n. Any element that's congruent to 1 modulo p to the n is a root of unity of order p to something. If that something is big enough, that's easy. So you get the inverse limit of 1 over MC mod p to the n, which of course remains 1 plus MC, which is the unit disk around 1, which is the points of the formal group. And as a matter of notation, from now on we will have occasions to base change a lot, and I don't want to carry this base change everywhere. So if G and G prime are over R, and we write hom S G G prime, I really mean hom over S of the base change. It doesn't have any other possible meaning. And since we want to discuss moduli, there comes the basic question of liftings, of, okay, not base changing, but doing the opposite. Okay, suppose we have R, which is an adic ring, J is enclosed ideal, and we have R over J. And given a formal group over R over J, can we lift it to a formal group over R? Can we find a formal group over R whose base change mod J, whose reduction is the one with which we started? And the answer for this is a very old one, was given by Lazare in 1955, I think. And this you can always do. That's very easy, and the answer is simply yes. The reason is not so easy. The proof is not so easy. Lazare shows that there exists a universal d-dimensional formal group law in a certain sense, but the important thing is that the universal ring over which is defined is a free polynomial ring in infinitely many variables. So every formal group law is obtained by specializing this universal one up to isomorphism. Okay? And of course, if it's free polynomial ring, you specialize them, you want to lift them, you just lift the specializations as you want. How about lifting isogenies? So here are 3 results that together we will summarize them by saying that quasi-isogenies are rigid. So let F and G be p-divisible formal groups over R, and it's very important now that we are dealing with p-divisible ones. And J, as usual, a closed ideal. I want it to be also topologically nilpotent. Then reduction of homomorphisms modulo J is injective. Okay, so the homomorphisms, say, over ZP inject into the homomorphisms over FP. But it's not true that the homomorphisms over OC inject into the homomorphisms over FP bar, because MC, by which you divide it, is not topologically nilpotent. So you should be careful when you apply this. This means that if you have lifting, the lifting is unique in this situation. Now, do we have lifting? On the nose, definitely we should not expect it, but if both J is nilpotent and P is nilpotent, then you can lift it up to a quasi-isogeny. And precisely if J squared is 0, of course, you can always iterate this and get any power of J being 0. But if J squared is 0 and P to the n is 0, then for any alpha, P to the n times alpha lifts to homomorphism. This is not a difficult result. And as a result of 1 and 2, if both J and P are nilpotent, then the quasi-homomorphisms in this category of p-divisible groups or p-divisible formal groups up to isogeny, the quasi-homomorphisms are the same over R and over R over J. And as I said, you must be careful when you apply it. Each of the assumptions that we stated is necessary. You can have counterexamples. So what do they look like? We have some examples, but what besides the examples that we have seen, or the examples that come from abelian varieties, it makes sense to start classify them by dimension, and definitely would like to take R to be simplest as possible, which would be an algebraically closed field of characteristic P, and then an old result, I don't know who was the first to prove it, says that for any height h, there exists up to isomorphism a unique one-dimensional formal p-divisible group h0 of height h. And this will play an important role in all that will follow. So how do we construct it? One way is to take, if you know about Lubin-Tate formal groups, if you've studied local class field theory, maybe you've come across them, you can take the Lubin-Tate formal group law over the ring of integers of the unramified extension of degree h of QP. For example, one that is associated to the polynomial px plus x to the p to the h, and reduce this one. We will later see how this one reappears as what's called the canonical lifting of h0. That's a very cheap way of constructing this h0 if you believe that it is unique. How about endomorphisms? Okay, if you accept what I just said, how to construct it, then the Lubin-Tate formal group law over zp to the h has zp to the h as endomorphism, so the reduction, of course, inherits these endomorphisms. It also has Frobenius of degree p, absolute Frobenius, because it's somehow defined over fp. You do not need fp to the h to define it. And if you look at the way Frobenius pi and zp to the h commute, they do not commute, but together they make up the ring of integers of the maximal order in the division algebra of invariant 1 over h over qp. And this is, in fact, the full ring of endomorphism. So this ring, again, will appear later more and more. And as an exercise, you can study this and figure out yourself which of the endomorphisms are defined over fp, which only over algebraic closure. So now I thought I would have 20 minutes. I have 15 minutes for the Lubin-Tate moduli space, but we finally come, after all this review and this basic results about liftings, to defining the first moduli problem to figure out in these lectures. So let K be algebraically closed of characteristic P. Let H0 be this unique one-dimensional formal p-divisible group over K. W, the Witt vectors over K, which is just the ring of integers in the completion of the maximal unramified extension of QP. And consider the category, I'm following Lubin and Tate, consider the category CK, which is the full subcategory of adic rings over W of local, complete, Noetherian rings with residue field K. And for any such R in CK, for any local, complete, Noetherian ring, I want to consider all the pairs G iota, where G is a one-dimensional p-divisible group now over R that reduces to H0, modulo the maximal ideal, but I want to consider it together with a specific isomorphism iota of the reduction with H0. Okay, that's the correct thing to do because it turns, okay, so this is a functor. It's a functor from the category CK to sets, right? Any map from R to R prime induces, of course, by base change, a map from the G iota over R to the G iota over R prime. And it is rigid, okay? It doesn't have any automorphisms, exactly because of this iota and because of what we said before about the injectivity of reduction, okay? What would be an automorphism of a pair G iota? It would be an automorphism of G over R, whose reduction commutes with iota, or makes a diagram with iota, but this means that the reduction should be trivial, okay, because it's the same. And this means that by the injectivity of reduction of endomorphisms, this means that the automorphism was trivial to begin with. The group of units of the maximal order of D acts naturally. How? You do not change G and you post-compose iota with delta, okay? So iota was an isomorphism from the reduction of G with this fixed model H0, but the automorphisms of H0 are just OD star. So you can change iota. And there is an important variant of this, which explains why I put the little 0 on top of M, in which you do not require iota to be an isomorphism, but only a quasi-isogeny. Now, because G reduced, G tensor K, is abstractly, of course, isomorphic to H0. It has no choice. It is of height H in dimension 1 over algebraically closed field. This iota is basically a quasi-isogeny of, in the variant, is a quasi-isogeny of H0, which is an element of D star. But D star is just, right, is OD star times the cyclic group generated by pi. Okay, that's structure of the units in this division algebra. So therefore, depending on what's the power of pi or what's the height of the quasi-isogeny, that's the same, you get a certain index I. So M is just a disjoint union of Mi for I running from minus infinity to infinity. And now you get the bonus that not only OD star, but D star acts. And this pi shifts Mi to Mi plus 1. And now comes the basic theorem of Lubin-Tate from 1966, that this functor M0, of course M would be the same thing, but Z copies of M0, is representable by a formal scheme, which is the formal spectrum of a very simple ring, which is the power series ring over W in H minus 1 variables. And I will say a few words later about how canonical these variables are. They're not canonical, but there's something to be said about them. And I'd like to sketch in the remaining time the original proof of this, or the main ideas that go into the proof of this. Both the paper of Lubin-Tate and a very good paper by Gross and Hopkins are highly recommended for this topic. They're both very readable, enjoyable, and short. Gross and Hopkins is not that short, but at least the representability is not long. And but let's first see some consequences. For example, if H is 1, there are no variables, right? H minus 1 is 0. This means that there is a unique deformation, and we know what it is. It must be the multiplicative formal group. So the multiplicative formal group is rigid. Another consequence, not consequence, but a remark to say, is that because OD star acted on the functor, right? Whoops, sorry, I wanted to use the laser. Here I have this thing. Acted on the functor. It should act on the formal scheme that represents it. But this action is highly non-trivial. And again, in the appendix to the paper of Gross and Hopkins, he's working out some formulae both for this and for the period map that we'll encounter later. And you can see how non-trivial these things can get. So, yeah. Yeah, G, well, height was associated to things in characteristic P, but the reduction of G is H0, so that should be the height of, yeah, okay. Height was something that was associated in characteristic P, but the height of the reduction is H, yeah. G is, yeah. Yeah, I should say, what does it really mean that it is representable by this ring? It simply means that for any R in this category CK for any local complete Noetherian ring R, once you fix the coordinates u1 up to uh-1, there's a canonical identification between pairs g iota and simply h-1 tuples in the maximal ideal of R. Remember that in this category, homomorphisms of adic rings should take the U's to topologically nilpotent elements in R, and these are, of course, elements in the maximal ideal. And that this is functorial. When you change from R to R prime, then things behave well. So let me quickly go over just a sketch without, there will be formulas here, but the formulas are really not important. First of all, these slides will be on the conference website, so you can always look at them. You can look up the literature. The idea is that somehow we start with a universal formal group law in infinitely many variables that we call V1, V2, and so on, that is built in the following way. We define iteratively polynomials bi, but they have denominators. Okay, they're in p to the minus I times zp with the v's. They involve, bi involves only v1 up to vi. And the formula that defines them should remind you of formulas that appeared or did not appear deliberately in today's talk on fit vectors, but these are very similar formulas. And you make out of these b's a power series f, which is a summation of bi x to the p to the I. Okay, so it has very sparse coefficients. And you use this f as a logarithm in characteristic 0 to build a formal group law f. Okay, so we've inverted p, so I haven't said it, but that is something I should have said, that in characteristic 0, you always have logarithms, and at least one-dimensional formal groups are just GA. There's nothing to say about formal groups in characteristic 0. But the funny thing, or the miracle that happens here, which is not such a miracle, is that despite the fact that you introduce denominators in these definitions, f has integral coefficients. Okay, so of course it involves the v's, but it is defined over ZPV. And this is a theorem of Lazard and Hazewinkel, that it is a universal one-dimensional formal group law over ZP algebras in the sense that any formal group law is isomorphic to one that is obtained as a specialization. Those that are obtained as specializations of this one are what's called sometimes p-typical ones. But the terminology is not so important. It's not that you get every formal group law, but up to isomorphism you get every formal group law. And you can say something about multiplication by p. Multiplication by p is congruent to vh x to the p to the h modulo p, all the v's below vh, v1 up to vh minus 1, and higher terms. But what this means is that if you specialize all the v's up to vh to be 0, v1 up to vh minus 1 to be 0, and you reduce mod p, then your power series begins with x to the p to the h, which means that the height is h. Now the v's are there's too many of them, and there's no unicity. Yeah, this is what I just said. But if you go now to our setup and you take this ring A naught, which is the power series ring over ZP in U1 up to UH minus 1, and you specialize, you want to construct a universal, something that would be a candidate to be a universal object there that would represent the functor of deformations. You specialize the first h minus 1 v's to your variables ui's, vh to 1, and all the rest to 0, then you get something, and you get a formal group law over that ring that you call H universal, its reduction is of the correct height, so you may just as well identify it once and for all with H0. It's one-dimensional and the correct height. And then you have to show that for every G iota, as before, where iota now is an isomorphism, that's in M0, there exists a unique further specialization, now specializing the U1 up to UH minus 1, which is all the freedom that we have left, in a unique isomorphism between G and the further specialization of that universal object to R, lifting this iota, so that if you reduce it modulo the maximal ideal of R, you get, on the right you get on the nose H0, and on the left you get GK, and you should get your thing. And this is what you have to show, right? This is what it means to be representable. And as always in deformation problems, the first step is to calculate what's called, I'll finish in 2 minutes, I just want to finish this topic, to calculate what's called the tangent space to the deformation functor. And this is when you evaluate the deformation functor not at k, where it's just a point, but at k epsilon, where this is the ring of dual numbers as before. And this is a fun exercise, because if you have such a G iota over k epsilon, you can view it, instead of over k epsilon, just over k, by restriction of scalars, so to speak. Or actually, yeah, that's sort of, you forget the epsilon, just, yeah. But then it becomes of twice the dimension, two-dimensional, and maybe twice the height, everything is twice. But it comes with a structure of an extension. And it's an extension modulo epsilon, of course, it's your H naught. So it's an extension of H naught by what? And the same argument that I gave you before about the Lie algebra being derivations, okay, tells you that it's an extension of H naught by Lie H naught. By the vector scheme Lie H naught, by the functor that gives you, view it as a functor that gives you simply the Lie algebra tensor, whatever ring you are at. But this is just the extensions of H naught by GA, tensor Lie of H naught, and we will later see tomorrow that the extensions of H naught by GA, by formal group GA, is the Lie algebra of the Cartier dual. So you get canonically the tangent space to the deformation functor being the tensor product of these two. And actually this is not unique to dimension 1. So in general, if D was dimension, if H0 was a dimension D, one Lie algebra would be of dimension D, the other one of dimension H minus D. So you would get a vector space of dimension H minus D times D. Here it's dimension H minus 1. So at least you get the right dimension for the infinitesimal deformations as from the number of variables that you introduced. It remains to be checked that in fact, via all these constructions, these variables do map to a basis, modulo higher powers do map to a basis of the tangent space. And this is the first step. And the second step goes under the general slogan of deformation problem is unobstructed. All that I want to say about it, if you're familiar with deformation problems, you have encountered it maybe in other contexts, but just as this involved studying of X1, unobstructedness involves the studying of X2 and in fact vanishing of X2. So the remarks are, first of all, read the paper, it's recommended. The whole theory extends to formal A modules if A is not ZP now, but any complete discrete valuation ring. P as a uniformizer is replaced by pi, the uniformizer of A, and P as the degree is replaced by some power of P, which is Q, etc. And this was done by Gross and Hopkins and Greenfield. And in fact, it works at the function field case too, if A itself is in characteristic P. And this leads to the important notion of trinitary modules. The U's are not canonical, but the point where they're all 0 is canonical. In fact, the subvariety where the first I of them are 0 is canonical, not really the use. And if you set all of them to be 0, you get what's called the canonical lifting, and you get back the Lubin-Tate formula group that plays an important role in class field theory, which over W is unique. Okay, remember that we're doing everything over the Witt vectors of an algebraically closed field. And finally, I'm over time, so I will not say anything about this question. You can ask when, if you have two pairs, G iota and G prime iota prime, that are distinct, when is G abstractly isomorphic to G prime? And this is rather easily answered by how many of the endomorphisms of H naught you can lift, or of the automorphisms you can lift to G. So this coset, or the quotient of the two groups of automorphisms classify this. Okay, so we will start tomorrow with Greenfield level structure and the full Lubin-Tate tower above the Lubin-Tate Moduli space. Thank you.